Hello and welcome to Learning with Miss Doherty. Today I'm going to walk you through one of my things for what I'm creating for my algebraic reasoning class. So I've just opened this one in videos instead of the 2025-2026 notebook up here because the 2025-2026 one is not syncing, and also because I want to post this out to the channel that you're watching now. So to show that I'm actually creating this on my own, we'll go through the process. So I need a new section because the Algebra 1 and Algebra 2 is from my CUDA software suggested order of content. So I'm going to start a new section here. I just came down the bottom and we're going to call this algebraic space reasoning. Okay, we've already used that enough, so I'll take it out. I'm going to ask it to create it, and it's going to create it. There it is, algebraic reasoning. We have an untitled page. We're going to come over here, and I want to click up here. Now, down here in my little corner, you will notice that I have under where it says English, and there's a line, and then an exclamation mark, and a little keyboard. Over here is a little microphone, and we're going to say that exponential functions, okay, without transformations. So I'm going to take that off because I do not want all that in there. I'm just going to take all these out. Exponential functions without transformations. I want this to be capitalized. Space, Shift, F. I want this to be capitalized because it is a title of what the video is actually going to be. And Shift transformations. Okay, so I have that created. All right, let's bring this down here. Come on. And I'm going to click on this again. I'm just going to create the script that I'm going to be following. So just really quickly here. Here's one. Today, we are going to cover exponential functions without transformations. Now, what I need to watch out for is that sometimes it likes to, because I add extra things that I don't want. It's okay, but I like that. All right, so every time I hit enter or a new line, it shuts my microphone off. So I'm going to read this today. We are going to cover exponential. Yeah, that's good. We will start with a table of values. The scenarios we are going to cover today are and I'm going to grab this. When the base is equal to 1. When the base is greater than 1. And when the base is less than 1. Okay, now I'm going to go in and fix what I need to on this because we are going to cover A, or E, and I want to put an exclamation, a colon after that because we have a list. And not the pace, but the base. So back that up. B is equal. To, and because this is a number that is less than 10, English conventions say that we should spell the word out. I'm going to put a comma there. When the base is greater than 1, that should be a comma. And when the base is less than 1. Right, I'm going to press enter, enter, enter. Vocabulary that will be covered in this lesson includes, I don't know why it says it. Okay, and this time I want equal to this. Initial value, base, exponent, exponential growth, exponential decay, stasis, x-axis, y-axis, domain, range, end behaviors, asymptote, okay, I knew I was going to have to spell that one. It's like, why even try? All right, so this is going to be S T O T E. Asymptote. There we go. Asymptote. All right, press enter. Maximum, minimum, so that basically takes care of everything that we're going to be covering. All right, so now let's see if I can insert. I do not have equations on here. I don't. So we're going to be drawing some of these. What we have over here in draw. I don't have anything over there. We've got new page color. I'm going to change my page color so it's light blue. I like the light blue better. And I want a grid line. So we're going to put some grid lines on here. And maybe I don't want the page color blue then. Let's try maybe a light green. That might work better. Okay, and let's go back to view paper. I want maybe slightly larger grid lines. It doesn't give me a chance to do different grid lines. Okay, that's great. Okay, and so I've got this script that we're going to be doing, and we're going to start out with writing a little thing right here. Come on. Why are you not? Stop. Okay. I can't do here. There we go. Okay, we are going to start with what happens if we have an exponential function, which is in the form f of x equals a parentheses b raised to the x power. And the base is greater than 1. Okay, and then we'll put some things in there. All I want to do is I want to change that because we have our scenarios. Come on. Go ahead, stop. So I'm going to actually grab this. Stop. So I want to erase that because I don't want that in there. Alright. So hit stop. And I'm just going to pick this up. Let's stop. I need to put the pen down. Because I hate me trying to draw. And I don't want to draw. I'm just going to select all of this. And I'm going to copy it. And I'm going to paste it down here. Paste. Well, I told you to paste. Okay. And say equal. I want that to be 2. Let's see if I can get that to paste one more time. And let's see here. There we go. Yes. Okay. So those are all my 3 scenarios. And I'm going to put in some more spaces here. And I don't want double rows of like that. Alright, so now I have this set up the way I want. And we're going to go through. Alright, so we have this equation here. And again, I wish I had, we have f of x. It seems to be f of x. F parentheses, f of, this must be lowercase x. Come on. Stop. I was trying to read that I have my pen picked up. And I will make these nicer before I submit it to, or before I show them to my students. Back up. X, and that should be italicized x, but that's okay. Again, I'm just showing this as how I do this really quickly. I'm just going to, so that we have it, that is f of x, and I'm going to write it over here to the side. What does that look like? That we have f of x equals a, and I'm going to move this over, oops, so a little bit, parentheses, b raised to the x power. All right, now we're going to go back and look at some of our vocabulary here. So this is our exponential function. And we have that this is our exponential function. And a is our initial value. And how I teach this to my students is I go, your initials begin at the beginning of your name. So it's what we begin with. B is our base. And x is our exponent. Okay. All right. So the rest of those, we need to actually do some equations and graphing before we can do anything like that. So we're going to start out with a table here. Until it stops. And some more space here. Oh, there we go. All right. we're going to start out with our function here, which is f of x equals b raised to the x power. And so I'm going to write down a table of values. So here's a table of values. We have our input, which is x, and then we're going to have our f of x, which I'm just going to again write it out as a parentheses b raised to the x power. In this case, we're going to say that we're going to start out with 1, and our base is going to be 2. So, because that's the next integer value greater than 1. So if I put in, I'm going to leave 0 for a minute right now because we'll go backwards on that one. If I put in 1, if I put in 2, and if I put in 3. So I'm going to put in that my value a is 1 times my base, which is 2. That is not going to change. And my exponent, that is what my x is going to be, raised to the first power. So that's saying I'm going to take 1 times 2 raised to the first power, which of course is 2. So I'm going to graph that out here in just 1 second. All right. Still have 1 times 2 raised to the second power. 1 times 2 squared. Well, 1 times 2 squared is 4. And then I have 1 times 2 raised to the third power, which is 1 times 2 cubed equals, well, we can come over here if you have to and do some side work. 2 times 2 times 2. 2 times 2, of course, is 4. Times 2 is 8. We can also notice that there's a pattern going on, that this is doubling every time. So as my exponents increase, this doubles to 2, this doubles, and so now we can figure out what it would be if x was equal to 0. So we would have 1 times 2 raised to the 0 power, and if I am going this other way, 1 times 2 to the 0 power, if I am multiplying by 2 to get my next one, so my next one would be 4. 1 times 2 to the 4th power would give me 16. So going the other way, I'll put down here 8, 4, 2, I would be dividing by 2 to get my previous value. So divide 2 by 2 and I get 1. Okay? So if we have a base that is greater than 1, which that is, if it is greater than 1, we can see that, not even just graphing it, just looking at our tables, we can see that our outputs are increasing. Our domain is going to be, should be, that we can put in any value. We can put in all real numbers, I think. Well, we'll see here in a minute, because we're going to graph it. And then our exponents, we can put anything in for our exponents. We can put in negative numbers, we can put in positive numbers, and then our range, well, we don't know about our range yet. That's where we're going to get our picture from when we get ready to graph this, okay? So our domain is our inputs, it's our x's, our range is our outputs. Now, before we go, we're going to now graph what it kind of looks like, sketch it out over here. That's why I put this graph paper up. So sketching doesn't have to be very pretty. Let's do this in colors. So we're just going to sketch it out here really quickly. I'm going to put 0 here. So when I 0, and then I had I'll go all the way to 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Here we go. Okay, so we come all the way up here to 16, and I'm just going to put every 2. So 1, here's 2, 3, here's 4, here's 6, 7, here's 8, 9, here's 10, 11, 12, 13, 14. And I'm going to just skip every 2 numbers. So here's going to be 1, and 2, and 3, and 4. So when we put in 0, change that to red, we have 0 and 1. And then from our table, we had 1, and we got out 2. So again, I'm looking at these also. I put in 2, I get out 4. 2, 1, 2, 3, 4. I put in 3, I got out 8. 3, 1, 2, 3. Come on. Sometimes you might want to figure out what those are. And then if I put in 2 to the 4th, we got out 16. So 4 and all the way up here to 16. And then I'm going to just connect those points together. Now we can see that we have growth as exponential growth. So this is our function f of x equals 1 times 2 raised to the x power. And again, we love our decimals graphing calculator. We're just going to come over here real quick. Come the decimals. And we're going to see what that looks like overall. So you can type in using your function f, and then I want parentheses x, and I want close parentheses. I want to do equals 1 times parentheses 2 close parentheses raised to the x power. And now I get a lovely picture on this. I can see that it is indeed, if I click on that point right there, it's going to give me the point 1, 0. I can come over here and I can go to my table of values. So I'll go ahead and put my label there. I'm going to go to my table of values. I want to go ahead and have those points in. I want to show that those are on there, and I want that point to maybe, no, it's not going to show up. But I can see that those points are going to be 1, 2, 2, 4. Now, we were graphing on the positive side of the equation. On the positive side of the quadrant, we were in quadrant 1. We need to go and look at quadrant 2, which is where x is negative and y is positive. So as I come over here, I am noticing some really interesting things here. I am noticing that it doesn't matter how far I go over, this never crosses down into a quadrant 3. It stays at quadrant 2. So I'm going to put in some numbers over here. This is one of the reasons I absolutely love decimals, because I can put in different numbers. I'm going to put in like -5, -10, well, not negative C, -10. Okay, what if I put in -7? Okay, I can see that as I'm going to go ahead and take that 10 out. Let's delete that, and then I'm going to come over here and delete that. That way I will get rid of that one. If I put in -7, I'm getting more zeros as I go. So if I put in like maybe -8. Okay, now I've got 2 zeros and a 3, and -9. I got 2 zeros and a 1, so I'm getting closer and closer and closer to 0, but I can never really get to 0. That is called an asymptote. It is a border. Okay. So when we're talking about end behaviors, let's come back over here. And let's go ahead and sketch this over here. We're not seeing this part of our function, so I'm going to use a different color to show that we're not seeing this part of the function. We're noticing that this is getting closer and closer and closer to 0, but it never crosses 0. So we have an asymptote, and there are 3 different types of asymptotes. There is a vertical asymptotes. There are horizontal asymptotes, and there are called oblique or slant asymptotes. So this is never crossing a horizontal line, so this is a vertical asymptote. And where does it occur? It occurs, okay, so we have to stop and think, what is our outputs going to be? What is going on with this? So my x's are changing, but my y's are getting closer and closer and closer to 0. So we have a vertical asymptote at the line y equals 0. I want to go ahead and show that. So if I come over here and graph that, because in Desmos I can go y equals 0, and I don't want that as the color. I want to change my color to green, and I want to make it thicker. I want to make it like butterfly. So as you can see, when I graph the line y equals 0, I can see that that is where my vertical asymptote is going to happen. It's going to approach, my function is going to approach 0, but it's never going to cross 0. It's never going to, my y's will never be a negative number in this case, okay? So back over here, we have vertical asymptote at y equals 0. So we have talked about our initial value. We have talked about our base. Why that doesn't want to change. Talked about our initial value. We've talked about our base. Our exponent, of course, is what our is the power that is changing what we're doing. We have looked at one that is exponential growth. Our x-axis, of course, is our right there. Y-axis is our y-axis there. It goes up and down. It's our horizontal, is our vertical and our horizontal axis. Our domain, well, our domain is that we could put anything in for our inputs. And our range, oh, we haven't talked about our range yet. So let's go back over to Desmos. Now my range, I cannot get a negative number out of here. I can't. So my range is 0 and greater, but I cannot ever get to 0. So because we have an asymptote at 0, where it's going to get closer and closer and closer to 0, it can never ever equal 0. So in this case, my range, let's go ahead and write these down. Let's bring these on over. All right. So we've got our domain. We can say is, now we're going to do this in 3 different ways. All real numbers. We're going to say that our range, and this is what is called inequality notation, y is going to be greater than 0. Will not be greater than or equal to 0. All right. So this is inequalities. Okay. Mathematicians, we prefer what is called set. We prefer interval notation. Because these are easy to type on the keyboard. All right, so all real numbers, we can never get to positive infinity or negative infinity, so we put in parentheses. Anything that is not included always gets a parentheses. So we're going to go from negative infinity. Now, if your keyboard does not have an infinity symbol, that we can positive infinity. You can also write that as negative INF period, comma, positive INF period. Or just negative with a negative sign, infinity, period, comma, and then INF period, comma. I mean parentheses. All right, with our y. All right, we are never going to get to 0. So that's where our range is going to start, is that it's going to be above 0, so it's going to be greater than 0, and then to positive infinity. Okay. Or from 0 to positive INF. Either one of those will work. And then we also have what is called set builder notation. Now, set builder notation is used when we have a discrete function instead of a continuous function. We have a continuous function right now because most parent graphs are continuous functions. So this is set builder notation. And you use set builder notation a lot in probability and statistics. So we are going to put down that our domain is the set of all real numbers, where x such that, that's what that line means, x is a value in the set of all real numbers. Period, and then we use a curly brace to close it. All right, and then again, curly brace to open for our domain, y such that y is greater than 0. So you can use anything to describe it, but that's usually what we do. We could say y is the all real numbers greater than 0. Or you could even say y is the set of all real numbers greater than but not including 0. Okay, so there's many different ways that you could do that. All right. And then our in behaviors of this, as we are looking at this, the two things it's going to say that as x approaches positive infinity, f of x is doing what? So we're going to be looking at this side of it. So we're going to go from here. So as x is going this way, what are my outputs doing? Well, my outputs is that they are going to positive infinity. Okay? And then as x approaches negative infinity, let's do that in a different color here. Let's do that in this blue here. What is our f of x doing? So it's going this way. Should have went ahead and highlighted that. Oh, I want that to be yellow. I want that to be yellow. I want that one to be yellow. There we go. All right. So can f of x is approaching 0. So that's what we're doing. We're analyzing what's going on. We do not have an x-intercept because it does not ever cross the x-axis. So we have no x-intercept in this case. We do have our y-intercept. Is that when x is 0, y is 1. Okay. So we do not want to put down y equals 1, because if we put down y equals 1, I'm going to show you the difference here. Okay. If I put down y equals 1, you'll see I will get a line. And we don't want a line. We want our intercept. So we're going to cross it out. And again, we're going to say parentheses, 0, comma, 1. Close the parentheses, and yes, I want to put the label on there. So this is what we're looking for. We're looking for that point. We don't want the line. I have people that will put down y equals 1. An intercept is a point. It is not a line. An asymptote is a line, but an intercept is not. Okay, back over here. So we have covered our range, our in behaviors, asymptote, at maximum and minimum. So we're going to come up with here something. I like that. Come up here. All right. We've got our range. We've got our in behaviors. We talked about asymptote. All right. Maximum and minimums. We can have absolute maximums, absolute minimums. But if I look at my graph, I can see that there's not a specific point at where it is just slightly greater than 0. And when we're talking about a maximum or a minimum, we're talking about a specific point where it's going to be an inflection point. We also call them turning points. We do not have any of those in this case. We can see that we are noticing that we have growth, but there is no specific individual point in which we have that just we're turning, we're changing direction of our function. Okay, and I'll show you the decimals over here. I'm just going to graph something real quick. If I have something like x squared, you can see that we do have an absolute minimum right here at 0, 0. We have to where it changes. It is decreasing. Our function is decreasing until we get 0, and then it increases once we go past 0. And we are always talking about our maximum and minimums as we are reading our graph from left to right. So from our more negative to our more positive, that is what we're going to be looking for. So if I am looking at my function here, it is always growing from negative infinity all the way up. Okay? So understand those two differences, that we do not have a single point where it changes directions, where it goes from growth, back over here, x squared, where it's decreasing in value and then it increases in value. Okay? We do not have that inflection point at 0, 0. We always have growth with exponential functions, if it is an exponential growth one. Okay, so we're going to find out what happens if we change it so that the base is equal to 1. So let's come over here. We're going to find out what happens if we do f of x, and our base is going to be equal to, start out with 1. We have 1, and our base is x. So if I take my table, f of x, and we put in x, and we put in 1, and we put in 2. I'm just going to put in a couple of them, and our function is 1 times 1 raised to the x power. And I start out with 1 times 1 raised to the first power. I get 1. 1 times 1 raised to the second power. I get 1. I get 1 times 1 raised to the third power. I get 1. So I'm just going to have a straight line. There is no growth. Let's come back over here. Come on, decimals. Come on. There we go. So I want to go ahead and hide these. I like that I can just hit those and just get them to go away. I'll go ahead and close out my table. I'm going to take that label out. Alright, so if I type in f of parentheses x equals 1 as my initial value, parentheses, 1 as my base, close parentheses, raised to the x power, I just get straight stasis. I get a line. There is no growth, there is no decay, and it's going to tell me, hey, you define, okay, I'm going to make this f of 2. F of 2. Right. So as you can see, it's just a lovely straight line. It is not going anywhere. It's not going up. It's not going down. It's just, woo. I can even change this color so that we can see that it is, as you can see, nothing. There's no growth. That's what it means by stasis. So, all right, come back over here. Stasis means no growth, no decay. Just stays the same all the way through. All right, so finally, what do you think is going to happen if our base is less than, okay, so I should have put it on there. I should have put it that the base is less than 1 but greater than 0. Okay, and there's a reason for that. So we are going to be seeing, we're going to do, let's do 1/2. So we're going to do x, and f of x is still starting out with 1. That's our initial value. And our base is going to be 1/2, and we're going to raise it to the x power. So we start out with 1, and then 2, and 3, and I'm going to scooch with 0 up here too. Okay. I know I should have left some more space, but that's okay. All right, so if I take over here and I put in 1 times 1/2 raised to the first power, that means I'm going to have 1 times 1/2, which of course gives me 1/2. If I take 1 times 1/2 squared, that is 1 times 1/2 times 1/2, which gives me 1 times 1 is 1, and 2 times 2 is 4. That's going to give me 1/4. And then finally, if I put down here 1 times 1/2 cubed equals 1 times 1/2 times 1/2 times 1/2. Well, we know this is 1/4 times another 1/2 gives me 1/8 times 1, which is 1/8. And again, this is being divided into 2 each time. So if I'm going to multiply this by 2, I'm going to get 1 times 1/2 raised to the 0 power. 2 times 1/2 is 1. So you know something really interesting? our intercept on both our growth and our decay will be 0. When we have 0, will be 1. That's one of the properties of an exponential function. So let's come back over here to decimals. All right, let's go ahead and change this one. And f of parentheses x equals 1. That's our initial value. 1 divided by 2. Arrow out so we don't keep anything in our denominator. Close our parentheses. We are going to raise it to the x power. And we can see that it has exponential decay. Now I'm going to go ahead and put, I want to make that as red. I want that to be a red color instead. Come on. Hold on to it and turn that. And I want that to be just slightly bigger. About 4. There we go. Alright, let's go back to our other one, which was our exponential growth, which was f of x, f of parentheses x, and the parentheses here. I don't want that. I want that to be green, because that's going to be growth. Okay, I want that to be 4. It's going to be equals 1, parentheses, base was 2, close parentheses, raised to the x power. Okay, so we got both of those in there so we can compare and contrast those. They both have the basically same shape. They both have an asymptote at y equals 0. They both have the same range. They both have the same x-intercept, the same y-intercept. They do not have an x-intercept. The difference is that our in behaviors has flipped. Our domain is the same, the range is the same, the in behaviors has changed. Because when we are looking at our exponential decay, as x is going to positive infinity, our f of x is approaching 0. As x is going to negative infinity, our f of x, our output, is going to be going to positive infinity. That's the only two things that change, is our in behaviors. Domain is the same, range is the same, asymptote is the same, y-intercept is the same, and x-intercepts we do not have on either one of them. All right, so that is what you see as an entire lesson for what I've covered. So we're going to go ahead and do our real quick run through here. So on this one, it is going to be exponential decay. Okay. And we're going to say no x-intercept. Y-intercept is 0, 1. We have our domain, and I'm just going to do it in interval notation. We are going to go from negative infinity to positive infinity. Our range is going to begin at 0, and it still goes to positive infinity. Let's see, asymptote. We have a horizontal one. Y equals 0. There is no maximum and no minimum. Okay, and then in behaviors, as x approaches positive infinity, f of x approaches 0, because remember it is a decay, and as x approaches negative infinity, f of x approaches positive infinity. Now, the reason, I don't know why it does that. So, the reason that we had to put a restriction on the decay to where it is between 0, but not less than or equal to 0. We don't want 0. We don't want it to equal 0. It's got to be greater than 0. X less than 1 is because we have two things. If I just strictly said less than 1, I could put down like -2 would be less than 1. So let's go see what happens when I put in the function -2. So I'm going to take and just hide these two. If I do my function f of x equals 1 is my initial value, parentheses, then -2, close my parentheses, and I raise it to the x power. Okay. It is not showing me anything. It is not showing me anything. It should show that I've got something graphed because I've asked it to do something. So let's go look at our table and see what our table is showing. It's giving me an error message. It says, oh, it says I have defined f in more than one place. Let's go ahead and do this as f3 of x now. All right. Still gives me an error message. You have defined, okay, how about if we just make this g? G of x. You can use different variables if you want to. All right, so we're going to get rid of this, and I'm going to bring this up. Okay, I have a mess here. I have all kinds of fun things. I'll go ahead and get rid of that and get rid of that. It has not graphed anything for me. It is going, I don't know what that thing is doing. It's going, -2, 0, 1. So you notice that we have something going on. This is what is called an oscillating function. So if I go over here and I type in 3, I'm going to get a negative number. Put in a +4, I'm going to get a positive number. We have an oscillating function, so we cannot have it to be a negative number as a base. Because when we have an exponent, when it is an even power, when that x is an even power, we're always going to have a positive number. So that's one reason why we can't just put in a negative number. All right. The other reason that I said that it's got to be between 0 and 1, if I put in this as an example, f of parentheses x equals, I'm just going to do 3/2, parentheses, let's see, 1, that's my initial value, parentheses, 3 divided by 2, arrow out, close parentheses, raised to the x power, because I had somebody say one time, if it is a fraction. Well, 3/2 is a fraction. It is a improper fraction. It's not a mixed fraction. It just is that my numerator is greater than my denominator, but 3/2 is definitely greater than 1. It's 1 1/2. So it's got to be a proper fraction greater than 0, less than 1. Because at 1 we have stasis, and if I put in 0 here, I'm going to have absolutely nothing. Because 1 times something raised to the 0 raised to the x power is just going to give me 0. I'm going to have nothing. From 0 on over, nothing. Okay? And again, if I change the color on that, hopefully that will show up a little bit better. Let's do it. Okay, so as you can see, I have nothing. So we want to stay away from 0. We want to stay away from 1, because 0 means that we are just going to be on the x-axis, and it's going to be parallel to our stasis one at 1. So for it to have growth or decay, it's got to fall within those parameters. Okay? All right. And if you want to find out what happens if we change something in that, follow along for the next video.